Let's now work through a fairly long example where we verify the divergence theorem by carrying out both integrals and seeing that we get the same answer. So in particular, let's let Q be the solid cylinder, which is bound by the surfaces x squared plus y squared equals 1, which is a cylinder about the z-axis with radius 1, and the planes z equals 0 and z equals 3. We're going to let S be its boundary surface oriented outward, and we're going to let F be the vector field, 2x, negative 2y, z squared. And then divergence theorem tells us that the flux of the vector field through the surface, that's a big S, the double integral over S of f dot ds is equal to the triple integral of the divergence of f dv. So first of all, let's see if we can figure out what the solid is. So we're inside a cylinder of radius 1. So let me put my axes in. Here's the x-axis, here's the y-axis, and z. So that's one of my bounds. I'm also bounded by z equals 0, which is the xy plane, and by z equals 3. So I'm just going to have a piece of this cylinder between z equals 0 and z equals 3. Now notice that the boundary surface is going to be made up of 3 different pieces. It's going to have a disk at the top, a disk at the bottom, and then it's going to have the lateral cylindrical sides. And I'll remind you that the radius of the cylinder is 1. So if I split it apart, I have the disk at the top, I have the cylindrical sides, and I've got the disk at the bottom. So think about a tin can or a can of soup, where you have the lateral sides, then you have the circle at the top and the circle at the bottom. Now I need to orient each of those so that it points away from the contents of the can. So the orientation has to be pointing into the air. So on this top surface, which I'll call S1, I need to be oriented upward. On this lateral side, at any point, I need to be pointing outward rather than inward toward the can. Let's call this S2. And then the bottom disk needs to be oriented downward. So it has to have a downward pointing normal. So when we carry out the integral over S, I'm actually going to have to integrate over those 3 separate surfaces and add the results together. Whereas over here, I will be able to do it in simply doing 1 integral rather than 3. So what I propose to do then is spend the next couple of videos carrying out the integral on the left-hand side, which I'll call LHS, and then we'll do a video where we carry out the integral on the right-hand side and check that we get the same answer both ways.